compare a few examples which has a larger radius, something like sodium versus nitrogen. Look at them on the periodic table. Well, sodium is one row down from nitrogen, but nitrogen is, like 10 or so rows, 11 rows to the right. So larger radius. This is down and to the left, so definitely that would have the larger radius. Something like, let's say potassium. Again, you should look at your periodic table to compare these. Potassium compared to, let's just say molybdenum. Look at your table. Molybdenum is actually slightly lower, which indicates it should have a larger radius, but potassium is to the left, which indicates it should have a larger radius. Well, which one dominates? Well, in this case, potassium is molybdenum is one row lower, but potassium is 6. Molybdenum is one period lower, I should say. Potassium is 6 rows to the left, though, so 6 to the left is going to dominate. Maybe it's easier to see. Let's compare, say, phosphorus to, let's say, sulfur. All right, you see phosphorus is to the left. That should be larger. How about phosphorus versus oxygen? Well, phosphorus is to the left and down. That should be larger. Let's compare phosphorus to, say, bromine. Bromine is one period down, but phosphorus is 2 rows over. So in general, I would expect phosphorus to be larger. Now, some of these are trends. I'm not going to try to trick you there with some of the exceptions that come out here and there, but these are trends we can approximate. I do want to show you like phosphorus versus, let me just go over here. We have more space. Phosphorus versus selenium. You can see if you can tell, maybe want to pause the video, which one of those will be larger without looking at the tables. And again, I think there's that selenium, not scandium. And to be honest, in this one, I have no idea. We can't tell. We don't have enough information. So we cannot tell which one of those is going to be larger. We can compare something like, well, this goes along the opposite diagonal, so we cannot tell going on the opposite diagonal. They're both the same distance in the wrong direction for the diagonal, so we have no idea. Fluorine versus a fluorine ion. Think about that and decide which one of those you think should be larger. If you get stuck on these, I always like to just go back to the basics. Protons, we've got 9 protons and 9 electrons. Here we have 9 protons, but 10 electrons. So more electrons, same number of protons, the same draw for the electrons. So we're adding electrons with everything else being equal. That should be larger. If we compare sodium versus the sodium ion, again, I'll look at the protons and electrons. Sodium has 11 protons, 11 electrons. Sodium ion has 11 protons. Of course, that can't change, and only 10 electrons. We have the same nuclear charge pulling in the electrons, but in this case, we have more electrons. So the sodium atom is larger than the sodium ion, but the fluorine ion is larger than the fluorine atom. So it depends on whether you have cations or anions. And I think it always helps to go back to looking at what subatomic particles we have. How about which one more easily forms a cation? Sorry about my writing there. More easily forms a cation would be lower ionization energy. So if we compare something like sodium versus magnesium, well, the trend goes up and to the right. Magnesium would have a larger ionization energy, so sodium means it takes less energy for sodium to ionize. If we compare potassium with phosphorus, well, potassium is way over on the left and lower, so potassium again phosphorus has a higher ionization, much higher ionization energy, so potassium is more easily ionized. If we look at silicon versus bromine, bromine is actually lower on the periodic table, but it's 5 spaces to the, or 4 spaces to the right. So lower means it has lower ionization energy. 4 spaces to the right means it has higher ionization energy. So this should have higher ionization energy. So silicon should be more easily ionized. So to form a cation. So again, we can compare elements. If you look at francium versus anything, sorry, a little sloppy there, but anyway, get the idea. France versus anything. This has the lowest ionization energy on the periodic table. It's the atom that more easily forms a cation versus any other element. Which one more easily forms an anion? Larger electron affinity, which really means a more negative value. The way it's measured, strong attraction for electrons is a more negative electron affinity. So again, we tend to compare, if we compare sodium versus magnesium again. Well, magnesium would have a larger affinity for electrons, so in reality, neither of these guys has much affinity at all. They don't form negative ions. Probably means a little bit more to compare nonmetals to nonmetals. They're the ones that tend to form negative ions. So, say carbon versus fluorine. Fluorine is actually the most electronegative, so if you pick anything versus fluorine, fluorine wins. It's going to form the most electronegative atom on the periodic table. Sorry about that. Fluorine is the most electronegative atom on the periodic table, so it beats everything. Oxygen versus, say, sulfur. Sulfur is farther down than oxygen. So oxygen has a larger affinity for electrons. Oxygen versus chlorine. Again, this is another one that they're in the opposite diagonal. Chlorine is 1 space to the right, but it's also 1 space down. So without looking at tables, we can't tell which one is going to be more electronegative. Which one will have the larger electron affinity. Now these trends actually help explain why atoms form the ions that they do. The higher ionization energy increases as you go up and to the right on the periodic table, which means low ionization energies more easily form cations. These guys, actually pretty much all metals tend to form cations. They have lower ionization energies than the nonmetals in the upper right. In the upper right, as you go to the upper right, except for noble gases, of course, the electron affinity, the attraction for electrons increases. So these guys, these nonmetals, have a stronger attraction for electrons, and that's why they tend to form negative ions or anions, because they want to, or they don't mind gaining electrons if they have that chance. So it shows you why, again, or it helps you remember the orientation of the trends. The guys up here form negative ions because they have a higher electron affinity. The metals, especially as you go farther down to the lower left, have lower ionization energies. They more easily form cations because it's easy to kick off those outer electrons. So they form cations or positively charged ions. So I hope that helps a little bit in understanding not just the trends, but how they apply. And this will actually help you also later when we discuss bonding in more detail.